Good morning, students. In this chapter, we will study about digitizing analog signals. Actually, we will have a brief introduction about the process of changing analog signal to digital, the process of sampling, and what is the sampling criteria, and how do we represent, for example, a digital signal using binary numbers, quantization and signal to noise ratio and digital to analog conversion. Okay. A device that transforms an analog signal, such as, for example, speech, music, or picture, into digital is called analog to digital converter. For example, our speech, when we are talking through microphone, it's changed to electrical signal, and we have analog to digital converter, which changes the signal from analog to digital. Computer technologies can easily process, store, or transmit the digital data. That's why analog to digital converters are very important. So we find analog to digital converters in many devices, for example, computers, CD players, our mobile phones, and many electronic devices. They have analog to digital converter. So for example, if I have here this speech signal, it is analog signal changed from acoustic voice to electrical signal using the microphone. And we have here analog to digital converter changing to discrete values, and then after that digitization changing to binary values. So this is the CD recorder. The CD recorder records the digital data as a series of dots on the CD. And when we are playing using the CD player, we are changing back from the digital signal to analog signal, and we can hear it through our ears. So this is changing back from digital to analog. So as I said, microphone, for example, is a sensor that detects the acoustic energy forming the original music or the original music or audio signal and changing it to electrical analog signal. So the electrical signal is converted to digital by analog to digital converter. The binary numbers are encoded as a series of tiny dots just below the surface of the plastic disc, as we saw from the previous slide here. So there will be a series of dots on the CD, that means. And for example, in the CD player, what do we have? In the CD player, we have a laser scanner. So this laser scanner is, we have proximity sensor in the laser scanner. You remember a proximity sensor, we said in the previous chapter, it will transmit energy, light, and then it will, the transmitter and the detector are in the same location, and it will measure, or it will sense the reflected signal. So a laser scanner or a proximity sensor in the CD player detects and interprets the dots as binary numbers. The digital to analog converter converts back the digital signal to analog electrical signal. The electrical signal, then it can be fed to an amplifier with a speaker to produce the original analog music. So as I said earlier, when we are sampling, we must answer two questions in order to perform analog to digital conversion correctly. The first one is, how often do we need to sample the analog signal in order to retain all the information it contains? That means, what is the sampling frequency, or how frequent we have to sample the analog signal so that if when we are reconstructing the analog signal from its digital, we have a perfect reconstruction. So that means we can be able to listen, for example, the music correctly from the CD player. So for that case, we need to have we need to sample at a specific sampling rate. There is a criteria for the sampling rate, which is depending on the highest frequency in the signal, in the analog signal. So the sampling frequency depends on the highest frequency of the analog signal. There is a criteria called Nyquist criteria, and we have to sample above 2 times the maximum frequency of inside the analog signal. So this one I will show you with example, for example, about telephone keypad by the end of this lecture. So this is one thing, how often we have to sample, or what is the sampling frequency. The other thing is, after we sample, how accurately must the resulting digital samples be represented in order to reproduce the original analog signal satisfactorily. That means after we sample, we have a discrete value, and how many number of bits are required to represent that discrete value. Of course, the higher the number of bits, the better, but we will be limited also by memory, or we have to save it. We have to save the data inside computer or other memory. So this is also depend on the space we have. And this process is called quantization. Quantization is a process that approximates an exact numerical value using a specified number of bits. For example, if I have a value, analog value 2.5, then due to quantization, if I quantize 2.5 to 2, then there will be an error of 0.5, and this error will affect the reconstructor signal. So quantization is also important. So the two things we have to be careful when we are changing from analog to digital are sampling frequency and quantization. Okay, now what is again sampling? Sampling means converting an analog signal into a sequence of discrete values by observing and recording the values of the analog signal at a set of points. For example, if the signal is a function of time, that means we sample at a specific time, So that's what is called sampling. So when we are sampling at a specific time, we have discrete values. So sampling is taking a snapshot of the signal at a specific time. That means the signal can be one-dimensional. For example, if it is one-dimensional, a function of time, for example, like audio signal, then the sampling is one-dimensional. It's a function of time. But the signal can be also two-dimensional. In what case two-dimensional? Two-dimensional, for example, images and pictures. Images and pictures are two-dimensional because we have, if we take an image, for example, we have x-axis and y-axis. So we have to sample across x-axis and across y-axis. So it depends on the two. Three-dimensional. Three-dimensional is, for example, if we have videos or movies. So a two-dimensional signal that varies over time dimension is 3D signal. So we have, for example, a frame, a certain frame, as a function of time. The frame itself is two-dimensional. We have x-axis and y-axis. So when we are sampling our sampling time, we need to select our sampling time carefully. the sampling time is related to sampling frequency. Why? Because sampling frequency, Fs, is equal to 1 over sampling time. Sampling frequency is equal to 1 over sampling time. So Ts is called the sampling time. For example, here I have a sawtooth waveform or a triangular waveform, and let's see how does the discrete values look like when we vary the sampling time. Here, if you see, I have sample here, I have sample here. They are very far apart. So that means we have a large sampling time. So these are the discrete values. If I want to reconstruct the original triangular waveform signal from the discrete values, it will be difficult. It's difficult to know the shape. So because the sampling time is large. Here I have maybe sufficient, and I have this. I can know that this look like a triangular waveform from this graph. Here I have I selected Ts very small. The sampling time is very small, means you see it's very clear that this is a triangular waveform. But however, I have a lot of samples. Then I will be limited by memory. So because we have to save these samples in a memory. So when we are selecting the sampling time, we need to consider both factors: our space, our memory, the size of our memory, and also we have to make sure that we should be able to reconstruct the original signal from its samples. So the choice of the sampling time is very important, Ts. If the sampling time is small, if it is too small, then it's possible to visualize the analog signal from the sampling points. If Ts is too small, very small, okay, very small, then more samples are extracted from the analog signal than necessary. So we have redundant information. So we call this dense sampling. And dense sampling can waste digital memory or space. So when we unnecessarily make the sampling time too small, then we will have a problem of digital memory, wastage of digital memory. We will have wastage of digital memory. If the sampling time is too large, we call it coarse sampling, too large. Then we may lose information. That means if we lose information, we may not be able to reconstruct the original signal from its samples. For example, in the case of the CD player, I cannot be able to have the original music or any audio signal, that means. So it may enable the audio CD to store 20 audio tracks, but they would not sound like the original analog recordings. So selection of sampling time is very important. So the sampling time is related to sampling frequency. We call it Fs. Fs is equal to 1 over Ts. The sampling frequency, the unit of sampling frequency is samples per second, or cycles per second, or hertz. Now, for example, if we have a digital telephony system, speech signals are sampled at 8,000 samples per second. The sampling frequency is 8,000 samples per second. What does it mean? One sample takes 1 over 8,000, 125 microseconds. Okay? So if one sample takes 125 microseconds, then I can know the sampling frequency. Sampling frequency is 1 over 125 microsecond, which is 8,000 samples per second. In audio CD or music, it is sampled at 44,000 per second, or the sampling frequency is 44,000 samples per second. That means one sample takes 1 over 44,000, which is equal to 22.7 microsecond. Sampling of images. Image, if it is two-dimensional signal, so we have x-axis and y-axis. A square grid is used to sample an image in 2 dimensions. That means if I, for example, divide the horizontal, the x-axis into vertical lines and the y-axis into horizontal lines, I will have a square grid. So each square grid, for example, has dimensions. For example, in the x-axis, I can have millimeter per sample, or in the y-axis also millimeter per sample, or inch per sample. So think of a square grid for an image, for sampling an image. An image is sampled by measuring the amount of light reflected from each cell in the grid covering the image. So I have a square grid. So in each grid, I have a cell. So the image is sampled by measuring the reflected light from each cell. For example, digital cameras operate in this way. The sensor in the digital camera measures the amount of reflected light from each cell, or from each cell in the square grid. The detector produces a number equal to the average amount of light within each cell. So the amount of the light level within each cell. The photo detector, for example, in the digital cameras. The sample value for black and white image equals the average grade level in the cell. Cells covering white image regions detect a lot of light and produce large numbers, and cells covering black regions detect no light and produce small numbers. So for example, the black is 0, we can say, and the white is very large number. So by measuring the reflected light from each cell, the digital camera can be able to sample the two-dimensional images. A laser scanner samples images by using a proximity sensor over the surface. This is, we said before, a proximity sensor has a transmitter and a receiver inside. So the transmitter transmits light, and the reflected light will be measured by the receiving sensor. White and black sampling regions or grid points produce 1 and 0. For example, the white region can be detected as 1 and the black region can be detected as 0. Fax machines. Fax machines use a scanner to sample an image at 8 points per millimeter. So the sampling rate is 8 samples per millimeter. Sampling three-dimensional signals. For the case of 3D, we have frames. A frame is a two-dimensional, you see, x-axis and y-axis. For example, an image in 2D. So I have a two-dimensional image here, or frames. Then the number of frames per second is the sampling rate. For example, this is in televisions or in digital movies. Digitized movie is a set of two-dimensional images that we access sequentially over the third dimension of time. The standard TV, for example, has the sampling rate of 30 images per second. 30 images per second. Each image has 720 cells in the horizontal axis and 480 cells in the vertical axis. So the total number of cells is 720 times 480. Okay, so one image is 720 times 480 samples per image, and we have 30 images per second. So if we multiply all this, we'll have 10,368,000 samples per second. Computer systems use a super video graphic adapter to produce displays having 800 times 600 cells. So That means we have an image or a 2D image of 800 times 600 cells. So every 1/60 of a second. Okay, so as I said, when we are sampling, we need to be careful selecting the sampling frequency. So how we select it? By looking the signal, the signal spectra. The signal spectra means the signal in frequency domain. How does the signal looks like in frequency domain? So, for example, the keypad row and column frequencies for a telephone. This is the standard telephone keypad. The frequency interval of the telephone network is from 300 hertz to 3300 hertz. So each time you press a certain button here, each time you press, for example, number 1, number 2, number 3, each time you press these digits, two frequencies are generated. If you see this table, for example, if I press number 3, so what frequencies are generated? 697 hertz, low frequency, and 1477 hertz, high frequency. So we need to connect the column and the row to get the frequency. So in the column here, 1477 hertz, in the row 697 hertz. If I press number 6, so I have 770 hertz and high frequency 1477 hertz. If I press number 8, I have low frequency 852 hertz and high frequency 1336 hertz. So whenever I press a digit, two frequencies are generated. Okay, so analog signal, which is a sum of two frequencies. So if I want to sample this kind of signals, I have to see the frequency spectrum. So what is the frequency spectrum? The frequency spectrum means looking the time domain signal in frequency domain, and it is helpful to select the sampling frequency. So the power spectrum or the spectrum displays the frequency content of a waveform. So the spectral indicates the power spectrum, or the spectrum indicates the maximum frequency value specified by Nyquist criteria. Okay, because what Nyquist says that if we want to reconstruct the original signal from each samples, you have to when you are sampling, you have to sample at least twice the maximum frequency or higher, 2 times the maximum frequency in the signal or higher. So that's why we need to see the spectrum. So for example, here is number 3. Number 3, it is a sum of two frequencies, 697 and 1477. So this is the analog signal. When I add this sine wave, for example, of 697 hertz and 1477 hertz, the sum of the two signals is like this. You can plot it by using MATLAB, for example. You can make a function of these two frequencies, add the two, and you have this kind of signal. This is time domain. And then if I see it in frequency domains like this, so if I sample this analog signal, and if I want to reconstruct the original signal when I do from digital to analog conversion, so I have to select the sampling frequency which is greater than twice of 1477 hertz. This is number 8. This is the analog signal, and in frequency I have here 852 and 1336. So again, when I sample, I have to select my sampling frequency 2 times greater than 2 times 1336 hertz. Okay, this is just a simple example how to the use of spectrum and how to select sampling frequency by looking the frequency spectrum. Okay, so that's all for today's lecture. We'll continue the rest of the topics in this chapter in the next lecture. And thank you for listening to this lecture.